Hello students, in this video we'll give an example of using the multivariable change of variable theorem. Let's consider a region D, and D is going to be the region bound by y equals x, y equals 2x, x times y equals 1, and x times y equals 3. So let's sketch this region and see what it looks like. So here's our region D. Here's x, here's y. And when we look at y equals x, so y equals x looks like this. That's y equals x. Here's y equals 2x. And then x times y equals 1 looks like what? X times y equals 1. That curve, x times y is equal to 1. And then here's x times y is equal to 3. It's above that. X times y is equal to 3. Okay? So my region D is going to be this region right over here, inside the intersection over there. That's our region D. Okay? Now, what's the idea? The idea is that I would like to find this integral. So let's write down what the integral we'd like to find. Let's find a double integral over this region D of 1 over 1 plus x times y quantity squared dy dx. What I can do to find this integral is the following. I can notice that if I look at this new variable x times y, if I look at this variable x times y, it looks like x times y starts at 1 and goes to 3, right? So as x times y ranges from 1 to 3, we get a whole bunch of what? New hyperbolas that look like they go through that region. Likewise, I can look at the variable what? I can look at this variable y over x. So that would be y over x is equal to 2, and this would be y over x equals 1. And so all the lines between y equals x and y equals 2x have that form. So I would go like this. Okay? So I'm going to change the coordinates. So what's my coordinate change going to be? My coordinate change is going to be, I'm going to let u be x times y, and I'm going to let v be y over x. That's my coordinate change. And so now, the one thing that becomes easier in this range is that now it's clear what's the value u going between. U starts at 1 and goes to 3. So over here, I know that u goes between 1 and 3. And what does v go between? V goes between 1 and what? So v is y over x. Y over x starts at 1 and goes to 2. So it goes from 1 to 2. So my region of integration from this really strange region has changed to a what? Has changed to a rectangle in the UV space. So this is a rectangle in the UV plane. Okay, excellent. Of course, my function is going to change really easily too, right? My function is going to become 1 over 1 plus u squared. Easy enough. So the trickiest part of this problem is to find out the differential changes, right? So let's write down now the differential changes. So of course, what's our rule for differential change? Our dy dx, or dx dy, is the absolute value of the determinant of this Jacobian matrix, which is dx du, dx dv, dy du, dy dv, du dv. Okay? And so now I need to find out what dx du is. Well, I don't have x solved for, so I have to take these equations over here and either solve them for x or implicitly differentiate them. So in this case, it's actually easier just to solve for them, although implicit differentiation will work just as well. So if I solve these equations for x, how would I do that? Well, what I would do is I would take u times v. What's u times v? It's x times y over x. The x's cancel, and you get that u times v is y squared. So y is what? So y is going to be u to the 1/2, v to the 1/2. Great. Well, if y is u to the 1/2, v to the 1/2, then u is equal to x times u to the 1/2, v to the 1/2. So that tells me that x is equal to what? X is equal to u to the 1/2, and then v to the negative 1/2. Okay? So let's compute our differential now. So what's our differential going to be? So this matrix over here, that's our Jacobian matrix J. So what's J going to be? Our Jacobian is going to be determinant of partial x partial u. That's going to be a 1/2 u to the negative 1/2 v to the negative 1/2. Partial f partial x partial v, that's a negative 1/2 u to the 1/2 v to the negative 3/2. And then partial y partial u is going to be 1/2 u to the negative 1/2 v to the 1/2 power. And then partial y partial v is going to be 1/2 u to the 1/2 v to the negative 1/2 power. Okay. And so let's compute this. Over here, I'm going to get a what? I'm going to get a 1/4. The u's are going to vanish here in the main diagonal. I get a v to the negative 1, so I'm going to get a 1/4 v to the negative 1. And then the off diagonal, I'm going to get a positive 1/4. The u's are going to vanish again, and I get a v to the negative 1 plus 1/4 v to the negative 1. So our Jacobian in this case is just 1/2 v to the negative 1. So now I have everything I need, so that's my Jacobian. So in other words, dx dy is what? Dx dy is 1/2 v to the negative 1 du dv. So now I can change our limits of integration and find the integral. So let's do so. So now the double integral over d of dy dx over 1 plus xy squared is going to be the integral. What is my u going to go between? My u is going to go between 1 and 3. My v is going to go between 1 and 2. And then dx dy turns into a 1/2 1 over v. So I have a 1/2 1 over v. And then this is going to turn into what? I'm going to have a 1 over 1 plus u squared. And then the first limits are my v, so I have a dv du. We can rectangular separate this because I have a product of functions of u times functions of v. So this is 1/2 the integral from what to what? V goes from 1 to 2 of just a dv over v times the integral from 1 to 3 of 1 over 1 plus u squared du. And now this is going to be easier. This is going to be the log of 2 over 1. So that's just the log of 2. So this is just 1/2 the natural log of 2 from that first integral over here. And that's going to be multiplied by what? That's going to be multiplied by, this thing is tangent inverse. So I'm going to have tangent inverse of 3 minus tangent inverse of 1. We know that tangent inverse of 1 is going to be pi over 4, but for simplicity, we're just going to leave this as our final answer to the double integral. So by changing the limits of integration, we were able to actually find a much simpler way to integrate this function, compute this antiderivative. Thank you very much.